All right, hello. So this was the Understanding Exponential Properties worksheet, and a lot of people had a hard time with this thing here. Um, and the idea here is to try to make a connection between the properties of exponents that we've been studying and word problems, because things usually stick better in your brain if you have some context instead of just a rule that gets written down on the whiteboard. And so right here, I'll take you through it. I'm going to skip a couple questions as we go, but I'll show you how to do most of this worksheet. So here we have tuition at the U of O since 2000. And the first question is this a linear pattern or an exponential pattern? And as soon as you read the word linear, you should be thinking of adding or subtracting the slope. If you hear the word exponential, you should be thinking of multiply or divide. So your question here really is, do these numbers to get from one to the next add the same number every time, or do they multiply the same number every time? It's usually easier to look at the adding. I can see that the first two numbers add. If I go from 3,800, I have to add about 226 to get to the next number. And then if I try to add 226 again, it does not land me on the next y value. So I can tell just by looking at the first several y values that it's not linear because I don't add the same number every time. It doesn't go plus 226 plus 226 plus 226. And you can especially see that over on the end here that there's a way bigger increase here. It's almost a 300 increase instead of being a 226 increase. And that's what happens with exponential growth, is that it gets more and more expensive over time. So this is exponential kind of by process of elimination, because I told you it was either linear or exponential, and we knew it wasn't linear. Looking at Kiana here, Kiana part B thought that the equation was y equals 3,800 times 226 to the x. And that would be a pattern that starts at 3,800 and that multiplies by 226 every time. And I hope we can all see, if you look at the y values in our table, the tuition, it's not getting 226 times more expensive every year. Those numbers would go from 3,800, and if I multiply 3,800, times 226, I get a huge number right there. Kiana is not correct. That is not how much tuition costs the next year. And so you can write something down that, oh, well, she thought of it as adding 226, but she wrote an equation that multiplies by 226. Part C is really important, that you want to figure out the growth factor by dividing any two y values that are consecutive. Y2 divided by y1 works just fine. You could do y5 divided by y4. As long as you are doing two y values that are right next to each other, that's what consecutive means, and it's the later y value divided by the earlier y value, you're good to go. So for this pattern here, your m, you can get it by going 4,026 divided by 3,800, and if you round that off, you get 1.06. You'll also find the same thing is true if I did 4788 divided by 4519.2. Any two consecutive y values have a growth factor of 1.06. And what that represents is a 6% increase, because 6% as a decimal is 0.06, and multiplying by a number bigger than 1 will increase your value. So the equation to model the tuition then is y equals 3,800 times 1.06 to the x. To check that your function works, like we've checked all year long, anytime you want to check, you just take values and you substitute them in for x and y. And this one, because we did some rounding, we're not going to get exact values, but I'm just going to choose these 2 points as my things to plug in. So I'll do the 2005 and 5072.8 first. 5072.8 is my y value, and I'm checking if that equals 3,800 times 1.06 to the fifth. And the reason I did a 5 instead of a 2005 is because the table shows the cost since the year 2000. And so 2005 is 5 years after. So I typed it into my calculator there, and I got 5085, which is a little bit off. And I was expecting it to be a little bit off because I rounded my m to 1.06. If I had used the real m value, which is that hard looking, that decimal right there, if I used that whole decimal, I would get a little bit closer to the exact value there. Okay? So, moving along, Saul chose the point 0, comma 3800, and so he would have written down 3800 as his y value, and seeing if that equals 3800 times 1.06 to the 0. Then that's exactly what we see right here in part G. And if we want to divide it by 3800 on both sides, we should see that that cancels out 3800, leaving us with just 1 equals 1.06 to the 0. And the point that we're trying to get across here is this right here, that anything to the 0 power is 1, and that it makes sense in the context of the word problem, because when you plug in x equals 0, you're saying there have been 0 years of tuition increase. And so you multiply the beginning tuition by 1 because there have been 0 years of increase. So anything to the 0 power is 1. It doesn't matter if it's x to the 0, it could be m to the 0, it could be y to the 0, it could be 5 to the 0. Any number to the 0 power is 1, except for the exception of 0 to the 0 power. We don't need to worry about that one. Now getting on to page 2, where we start talking about negative exponents. I'm going to get through this a little bit quicker. The idea here is that if you want to find the year 2001, that's 1 year after 2000. So you just type it into your calculator, put a little positive 1 right there as an exponent. For the year 2002, you plug in 2. For the year 2050, you plug in 50. For the year 2100, you plug in 100. Now, the thing that gets interesting is when we start talking about going backwards, going before the year 2000. So in the year 1999, that's 1 year before 2000. So it's negative 1 years after 2000. And same idea, 1996 is x is negative 4, 1990 is x is negative 10, 1950 is x is negative 50. And you can plug those same numbers in to that same exponent, just like we did when x was positive 1. And so the sentence here that you're supposed to write down about how positives or negatives work is that positive numbers represent times in the future, and negative numbers represent times in the past. Down here, this is a really important sentence to be able to pull out. When you see an equation like this, you should be able to say it as a complete sentence. I see this sentence as, I started out paying $3,800 and I paid 1.06 times as much each year. And that's a 6% increase. And if I wanted to work backwards, what I could do is, instead of multiplying by 1.06, backwards multiplying is dividing. And so I can just take my 3,800 here and divide it by 1.06. So if I just take 3,800 and divide by 1.06, that predicts what the tuition would have been in the year before 2000. So 3584, I'll just kind of round it off. Then I just divide by 1.06 again, 3382, just rounding, do it one more time, 3191. You can see how it gets quite a bit more expensive as you move forward in time, and then obviously gets less expensive as you move back in time. We already knew these answers here, and we just get them by multiplying by 1.06 over and over again. Okay. And the big takeaway from this is summarized right here, that negative exponents are the same as dividing. Negative exponents are backwards positive exponents. And so positive exponents are multiplication. Backwards multiplication is division. Okay, so I'll pause right here because the fraction exponents and roots is something that we aren't focusing on this year. This is a really great activity to finish out if you are doing pretty well in this unit. You don't need to really worry about uh, you don't really need to worry about it too much. I'm not going to have the fraction exponents on the test, but it is something you'll see down the road. So please comment or ask questions if there's anything I can do to help. Thanks.